And if you recall, the area of a rectangle is just its base times its height. Area of a triangle is just 1/2 of its base times its height.
I thought rectangle was length by width.
Sure, length and width.
Well, it's the same thing.
Just depends what you want to call it. We'll call it length and width. Base and height, the same concept.
What's the difference?
Parallelogram. We said we're going to take the base and the height and multiply them together. Recall that yesterday we argued that this is the formula because we could say take any parallelogram and just cut off, draw an altitude, and just kind of cut off that right triangle and fit it in on the other side, and we should end up creating a rectangle out of it. And the rectangle's length and width were just the base times the height, or the distance between the two sides. As promised, we're going to explore some other figures here. So we're going to start by looking at trapezoids. Recall that a trapezoid is a quadrilateral that has exactly one pair of parallel sides. And if we drew just like a general trapezoid, here's a general trapezoid. Can I draw a trapezoid on this? No, I can't.
Oh, that didn't. Oh.
Here's a general trapezoid.
Wait, that is not. Wait,
That's a parallel.
Our trapezoid has exactly one pair of parallel sides. Note that these sides are clearly not parallel.
Like this. Like this, as longer than this.
We're gonna label, folks. We're gonna label the parts of a trapezoid. Namely, a trapezoid has the parallel sides we call the bases, and there's two bases. There's base 1 and base 2 of our trapezoid. And another important quantity is just like in a parallelogram, the distance between the two bases, which we'll call the height. So we have the two different bases, the sides that are parallel, and we have the distance between those two bases, which is called the height.
Oh wow,
All right. I'm going to try to do something kind of fancy here. So notice that what I've done so far is I've taken the trapezoid. I've taken our little trapezoid here, and I've duplicated it. I've made a second. Okay? You can't do this. I'm going to do some manipulating here. So whatever the area of this thing is we don't really know off the top of our head. But we do know it's got some area. Well, if I duplicate it, I get twice as much area. Do you agree?
yeah.
Watch what happens when I do this. I'm going to take this trapezoid, and I'm going to flip it upside down. I'm going to rotate it. I know you don't have that function. And if I fit it in exactly like this, what have I just made? Parallelogram. I've made myself a parallelogram. What's the length of the base of this new parallelogram?
B squared.
No.
Forget that. B plus A.
Well, this chunk was B1, and now I've moved it down here. This chunk is B2 and I moved up here. B1 plus B2, and it's being argumentative with me. There we go. So now the base of this new parallelogram that I've made is B1 plus B2. What's the formula for the area of a parallelogram? Base times height. So the area of this parallelogram that I've made should be exactly of new parallelogram is the base, which is b1 plus b2 times its height. This base times the height is the area of my new parallelogram. Is that the same as the area of my original trapezoid?
Oh.
This expression gives me the area of this whole figure, but I don't want that. Yeah, it's exactly. This is actually twice as big as what I need. So therefore, the area of the actual area of the trapezoid I'm looking at is half of that. So the area formula for a trapezoid, area of a trapezoid, is equal to half of that expression. Half of, add the bases, and multiply by the height. If you call b1, b2, and the distance between the two is the height, and then the area of that trapezoid, as argued above, by creating a duplicate, rotating, making a parallelogram, finding the area of the parallelogram and dividing it in half, is the area formula for a trapezoid. Okay. Add the length of the bases, multiply that number by the height, and cut it in half. Divided by 2. And this is true. Notice that this was in general. This was not just for isosceles trapezoids. This was not just for a specific trapezoid. This is for any given trapezoid, is the argument here. So whatever trapezoid I have, we're good to go. And again, it must be a trapezoid. So I have to have a pair of parallel sides, namely the bases. So if I throw some trapezoids at you, you could, like we did yesterday, you could, if you had the ability, if I gave you enough information, you could try cutting this into smaller rectangles and triangles. Or we could use this argument that we just had above and directly calculate the area in this fashion. So for example, our first trapezoid here, if I know our first base, one of the parallel sides is 3, well, the other parallel side is 7. The distance between them is 4. You could label these things if you wanted. Therefore, the area of these trapezoids must be what? Area half of 3 plus 7 times 4. 10 times 20, yes, square units. Unit squared. Order of operations, 3 plus 7 is 10. 10 times 4 is 40. Half of 40 is 20 square units. Same game with this trapezoid. You could say, find the parallel sides. Those are the bases. The distance between them at a 90-degree angle is the height. Therefore, the area is half of 6 plus 8 times 6. 6 plus 8 is 14. 14 times 3 is what, 42? 42 square inches, or square units. $42 square units. Okay, trapezoids.
This is easy.
Don't say that.
Our next, we're going to actually combine the next two together. Look at kites and a rhombus, because they both have a very particular property. If you recall, a kite and a rhombus both share this property. Do we recall what the property is? What property what their diagonals of a kite and a rhombus both share? What's true about the diagonals of a kite and a rhombus? For a rhombus, it's bisected, but a kite not necessarily. What do we know? But something is true between both of those two. Yes, Alyssa was nailing that. The diagonals of both a kite and a rhombus are perpendicular. So it may not look like it on my little sketch here, but they're both perpendicular. Namely, we've actually made we can actually draw in 4 right triangles. So we're going to come up with a formula that's going to talk about the size of these 4 right triangles. One way to think of it is actually, one way to think about this is maybe to look at the size of the diagonals themselves. Since they're at right angles, the area for a triangle is just 1/2 its base times its height. If you could come up with the areas of these 4 things are, then we could just add them together. For any kite, or for a kite in particular, note that one of the angles, another property of a kite was that one of the angles was bisected, namely the angles that are between the two congruent sides. So if this was a kite, then those two have to be congruent. The angle that's included between the congruent sides is actually bisected by the diagonal, which actually forces at one of the pairs of heights of one of the pairs of diagonals to bisect itself, which is kind of a nice little tool. For a rhombus, both diagonals are bisected. For a kite, one of them is. We're going to try to use this area formula and apply it to this kite. So what we end up getting is an important part of a kite or a rhombus is the length of diagonals. So if we think of this diagram is getting kind of complicated. We'll simplify it in just a second. If we think of, say, one of the diagonals having length, say, real creative here, D1 for diagonal 1, the other one having length of, say, D2, then the area of, say, one of these triangles should be 1/2 its base times its height, or 1/2 of, say, the diagonal 1 times half of the second diagonal, which forces, let's see, so the area of one of the triangles is half of one of the diagonals times half of the other diagonal. And half of this diagonal is the height. This full diagonal is here, and then it's a triangle. There's here. Well, how many triangles are there? Well, excuse me. How many of these big triangles are there? Because this is the area for one of the big triangles. So there's 2 of them, right? So if we added them together, what if I doubled both sides? So let's see. Half of D1, let's simplify this a little bit. That's what? Twice of 1/4 of D1 times D2. What's 2 times a quarter? What's twice as much as 1/4? Half. So the area for a kite and or a rhombus is exactly half of the product of the 2 diagonals. Where the diagonals are the distance between them. This works for kites and rhombus. Again, it's based off the fact this is a right triangle. These are right angles. They're perpendicular. It applies to both of these because they share this perpendicular diagonal property. Okay. Yeah, I could have just told that to you. Yes, I could have. But then again, maybe if you forget the area formula, you can actually work backwards. But maybe you have a chance to actually try to derive what this formula is. These formulas come from places. They aren't made up out of thin air. Namely, like Greece and East Asia, generally are the 2 credited with a lot of these mathematical formulas. So if I need to find the area of these some figures here, namely example A is a rhombus. This chunk here is 8. This chunk here is 3. What do we know about the diagonals, or what's another property of the diagonals of a rhombus? What do we know about this? What else do we know besides they're perpendicular? I think someone said it earlier.
Wait a minute.
Yeah, right. I thought you were one of them.
Thinking, I didn't raise my hand. I was like this.
What else do we know? For a rhombus, diagonals not only are perpendicular, but what else are they? Well, how else do they compare to each other? The two full diagonals are not congruent.
Well,
They are bisected. These two diagonals are bisected by each other. So this is 8, and that's 8. This is 3, that's 3. So then if I want to use my formula, what's the length of each of those two diagonals?
8 and 3.
What's this length here?
Oh, that means that.
That means that, say, one of the diagonals is 16. The other diagonal has got to be 6. That's 3 and that's 3, the whole thing's 6. This is 8, that's 8, the whole thing's 16. So then the area of this is half of the product of those. Half of 16 times 6, which is
96. Oh, half. Oh, that's
half of 96.
48. That's it. Wait.
Half of 96, which is 48 square units. You can apply again. I'll just tell you what the length of diagonals are. The second one. The third one, you have a kite. But we do know from the argument a property of kites is that the angles that are bisected, that's that other diagonal is, it bisects, the diagonal intersects. So one of the diagonals will not be bisected, but the other one that connects the two angles that are included between the non-congruent sides, that diagonal is bisected for a kite. So that's 4, and this is also 4. So you have one diagonal that's length 14, one diagonal that's length 8. (14 and 8). 7 times 8 is 56. Lastly, we're going to assemble a kite. Let's say we're assembling a new kite. The details on the container state that the kite has an area of 270 square inches. And the length of the vertical diagonal is 30. We'll find out why this thing is. There's a kite. I know that the vertical diagonal has length of 30 inches. I know it has an area of 270 square inches. I want to know what the other diagonal is. I want to know how wide this thing is. Well, you can use the kite formula and say 270, it's got to be half of 30 times the other diagonal. Half of 30 is 15. Therefore, if you divided this side by, say, 15, and this side by 15, 270 over 15 should be the length of D2. And what is 270 over 15? What is it? 18? And the unit that goes along with it is inches. So let's say second diagonal of 18 inches. So we've added 2 new formulas today. We actually derived both, so if you forget the formulas, you should be able to at least have a base to start to try to recover and figure out what the formulas actually are. Kites and trapezoids, rhombus included in there. There we go.